So with that, we will go to next presentation from University of Washington. Dr. John Stanton is going to present on developing prestressed concrete girder cross sections for longer spans and new materials.
The project is about new and optimized cross sections for lateral torsional roll buckling. And the basis of the project is that for longer spans, you need bigger prestressed concrete girders for bridges. But there is a real problem as you go to longer spans with the bigger girders, which is that they become increasingly difficult to transport and get to the site. And so the objective of this project is to say, can we create a girder cross-section which will satisfy several criteria, one of which is it obviously has to be strong enough and stiff enough to provide the kind of in-service behavior and performance that you would like. And to some extent for that, you just build a bigger girder. But there are several other criteria that you need to look at as well, one of which is, can you get it to site without having it suffer instability? And that turns out to be an increasingly difficult problem as you go to longer and longer girders. And there's just a couple of examples there. I noticed in Mohammed Mustafa's presentation, he showed a UHPC girder for 300-foot spans, and I can almost guarantee that that thing would never get to site because it's just way too tall and skinny, and it would buckle before you could ever get it onto a truck. So that turns out to be a major problem. There are other questions in addition to strength and serviceability in service and the stability question, also questions of cost and constructability. Can you actually build these things? Can you truck them? So these are the multiple criteria that we're going to have to look at. Now, we have not yet been able to start on this project specifically, but we have done a huge amount of work in terms of developing tools which will enable us to look at the stability questions in detail. And we did that under a separate contract. And that is primarily what Hank is going to talk about today, because that is one of the big inputs into this question of developing new and optimized cross sections. So I think with that, I'd like to hand over to Hank, who's the one who's been doing the real work on the project. Hank, over to you.
Yeah, great. Thank you for that introduction, Professor Stanton. And would you mind flipping over to the next slide?
Yeah, I can do just exactly that. There we go.
Great. Yeah, thank you. So as Professor Stanton alluded to, the main goal of this project is to develop new cross sections that really have optimized performance considering lateral instability. And recently we have seen issues with long span prestressed precast concrete girders that are having lateral instability issues during transportation and handling, namely excessive rigid body rolls and also twists at mid-span. So what we want to do is develop these new cross sections and primarily evaluate their lateral stability behavior, considering these instability mechanisms that are listed below in this scope section, which I'll be going over shortly as well. And additionally, while we first and foremost want to ensure that these potentially new girder cross sections have great lateral stability performance, we also want to ensure that the new girder cross sections are effective during service life and maintain adequate strength, but also that they're able to be easily fabricated, that they're constructible, and that they're cost effective as well. Professor Stanton and we, along with the previous grad student, Bill Galick, and myself, have done a fair amount of work developing the theory behind, some of the theory behind these instability mechanisms. And so we intend to extend that theory towards evaluating these new cross sections. And to do that, we plan on conducting a parametric study on the changes to these girder cross sections and the changed girder parameters. And so with that, we could flip on to the next slide, and I'll go into a quick overview of the girder instability mechanisms we'll be considering during this parametric study. And that begins with kind of the baseline simplest case we're examining, which is lateral roll buckling. And we can begin here by looking at this girder shown here on the left. And we can imagine a girder that is lifted from the top flange at an eccentricity to the center of mass of the girder at the midspan. So what we have is a lever arm between the reaction at the top flange here and the self weight, which is at the center of mass of the girder. And that lever arm between the reaction and the self weight leads to the girder being out of moment equilibrium. And so to satisfy moment equilibrium, it's going to progress to step 2 here, where the girder is going to roll to this initial roll angle. And if we imagine that the girder isn't going under any bending deformations yet, this is the roll angle, a rigid body roll that the girder would undergo to satisfy moment equilibrium initially. But then the girder is not going to not undergo bending deformations. So we're going to step over to this step 3 here, where the girder is going to then have a component of its self-weight acting perpendicular to the girder web, which is going to cause the girder to bend laterally. And when it bends laterally, that causes there to be a greater lever arm between the reaction and the self-weight. And that greater lever arm then will cause the girder to roll further, which will in turn cause a greater component of self-weight acting lateral and perpendicular to the web, which will then in turn cause greater roll, and so on and so forth, until the girder will either stabilize and find an equilibrium position at some rolled configuration, or it will continue through this loop until it buckles. And that really is the basis of lateral roll buckling behavior, which is kind of the baseline of the lateral instability mechanisms we'll be considering. And it's also important to note that the lateral roll buckling is a function of the center of mass of the girder. This dashed shape is what you would see on an end-on view as the maximum midspan deflected position of the girder. But lateral roll buckling and the other instability mechanisms we'll consider really depend on the position of the center of mass of the girder, not the maximum position. And that's represented by this black dot here. And could you go to the next slide, please? Great, thanks. Yeah, so the previous slide was just investigating kind of the most basic lateral instability mechanism, which is just the roll component of deformation and lateral bending. And I'd only mentioned lateral weak axis bending, but we could also incorporate strong axis bending and camber as well into the lateral instability behavior. And strong axis bending, essentially, we neglected weak strong axis bending on the previous slide, and strong axis bending will lower the center of gravity, and while maintaining the same lateral bending deformation, lowering the center of gravity is going to reduce the roll angle that the girder sees. So strong axis bending and incorporating that effect is stabilizing on girder behavior. Camber, due to pre-stressing, is very similar to strong axis bending, but in an opposite direction. The camber due to pre-stressing will raise the center of gravity of the girder, therefore destabilizing it. Additionally, we consider for our instability mechanisms the effects of overhangs due to lifting loop placement. And essentially the negative moments in the overhangs counteract the positive moments in the central spans of the girders. And that balance there then lowers the average deflection of the center of gravity of the girder, and is in the lateral and the vertical direction. And this is a very, very stabilizing effect. And overhangs are one of the best ways to combat girder instability. And the final instability mechanism that we'll consider in our parametric study to evaluate new girder cross sections is torsion. And the previous slide only showed the girder rolling and laterally deflecting, but torsion will soften the girder and essentially add an additional twisting component to that roll. So the girder will be twisted and rolled over further than it was before. And this is a destabilizing effect, and it is especially prominent at higher loads and longer lengths. And we're able to combine all of those effects together into a critical buckling load, which takes kind of this baseline buckling load, which is derivative of work done by Robert Mast in the 80s. And we're able to account for these other three instability mechanisms by simply multiplying that baseline buckling load by a factor that accounts for strong axis bending and camber, a factor that accounts for overhangs, and a factor that accounts for torsion as well. And we will include all of these instability mechanisms in our parametric study also. Could we go to the next slide, please?
Just coming, Hank.
Great. And so to actually perform the parametric study, we need to be able to predict what the final roll angle of the girders will be and analyze them somehow. And to do that, we have a couple of different methods. The most sophisticated and detailed and able to produce the most results we have is a numerical model that we've called rollbuck. And what rollbuck essentially does is you input this girder shape and layout into the program, and it then takes that girder shape and it does a process very similar to that shown for the kind of the lateral buckling slide I showed a few slides ago. And it then takes that shape and it'll essentially kind of freeze it and not allow any bending deformations, and it'll roll the girder until it finds a equilibrium position in terms of moment equilibrium. And from there, it'll unfreeze the girder, and then it'll allow the girder to bend and go through the strong axis bending, the weak axis bending, and then additionally torsional deformations as well. And from there, then we have a new shape, and we're back at the beginning of this loop, and we're able to re-enter the loop and roll and find a new equilibrium position, and then bend again, and so on and so forth, until the girder converges to a final shape. And with that, we're able to, with that rollback program, we're able to determine what the final roll angle will be for a girder anywhere along the span at really any load, applied load or length, while accounting for all of the instability mechanisms previously mentioned. So it's a very powerful tool to be able to predict the final roll angle of a girder. And currently with rollback, we have previously only considered linear elastic uncracked sections, but we're currently working on implementing the effects of cracking right now. And we'll be able to get that up and running, but we're currently testing that and developing that. And can we move to the next slide, please? There we go. Additionally, we have two other methods for predicting the final roll angle in a girder, and they're kind of moving down in sophistication level. We have the rigid link model, which is diagrammed, the setup for it is diagrammed here on the bottom right. Essentially, we take representative stiffnesses of the girder in the lateral, vertical, and torsional degrees of freedom, and we boil those stiffnesses down to springs of representative stiffness that support a node, which has essentially the weight of the girder boiled down to just that node. And from this setup, we're able to develop a potential energy formulation. And then by minimizing potential energy and arriving at equilibrium equations, we're able to do algebraic manipulations to arrive at this equation shown here on the bottom left, which is our rigid link model equation. And from that, we're able to determine what the final roll angle of a girder will be given a known applied load Q, a critical load Q critical, and an initial roll angle, all of which are known. So from those three quantities, we're able to pretty quickly and easily arrive at a final roll angle without having to perform a numerical analysis through rollback. Additionally, we can arrive at what is called we're calling the simple amplification equation, and from that we can get it directly from the rigid link model by making a small angle assumption such that the tangent of phi is equal to phi, or approximately equal to phi, and the cosine of phi is approximately equal to 1. And we're able to arrive at this simple amplification equation, which is able to predict the final roll angle of a girder explicitly off of the initial roll, the applied load, and the critical load. And we're able to get that directly from the rigid link model or from algebraic simplifications from the equilibrium paths of the girders and critical loads. So it was a nice verification that we're able to get these results from a couple of different places. Yeah, and I should also note that we're able to, the rigid link model and the simple amplification match the rollback results very closely. But moving on here, we just kind of zoom back out a little bit and ask, why are we seeing stability issues in long and deep girders, and what's really motivating this? And if you had a very long span, you'd have increased gravity loading, and so naturally you'd want a deeper beam. And if there were no lateral instability problems, that would be great. You could just have a deep beam. However, to make these deeper beams, frequently the girders are just made taller, but not made wider in the flanges of the webs at all. So this leads to increased strong axis stiffness, but practically the same weak axis stiffness. And this lower relative lateral or weak axis stiffness combined with the longer spans has led to lateral instability issues, and hence the need to possibly develop new cross sections. And some attempts to correct this have been to either increase the width of the top flanges of the girders to increase the weak axis stiffness, or to possibly even add temporary top pre-stressing strand and larger overhangs to essentially make the girder more stable, but also manage the tensile stresses in the top flange. And I'll move on to the last slide here now. And so our procedure for determining our optimal cross sections will be a parametric study. And that parametric study is going to run through a bunch of different new cross-section options. Primarily, that'll be examining whether or not we should widen or deepen the flanges or the webs of the girders, or possibly even whether or not we should construct new or different shapes that are possibly different than what's traditionally used, but could provide much better lateral instability performance. Additionally, we intend to look at material parameters such as concrete density, which could trickle down and affect compressive strength and modulus of elasticity through, how they're all linked together in the code. Additionally, we could examine miscellaneous different solutions as well, such as temporary bracing during transportation and handling, or even possibly kind of outside of the box solutions, like maybe turning the girder into a quasi HSS section in susceptible areas like the midspan by kind of creating a boxed up torsionally stiff section, or possibly even new temporary pre-stressing strand arrangements that allow for large overhangs without tensile stress limit issues in the top flange of the girder. And with that, I think that concludes it. Thank you guys for your time, and I'd be happy to answer any questions that you may have.
Thank you very much, Dr. Stanton and Hank, for the nice presentation. It's kind of eye-opening with that very tall. You usually don't expect the concrete girders have a lateral stability problem. So related to that, there's a question asking what you explained as lateral buckling for these prestressed concrete girders. How is it different from classical lateral torsional buckling?
Yeah, great, thank you. That's a great question, and happy to answer that and shed a little more light on that. Classical lateral torsional buckling, the girder is essentially fixed upright at the supports. It is not allowed to undergo rigid body roll. It will just twist along the length of the girder. And in this case, when we're looking at just lateral roll buckling, we're saying that there's no twist at all along the length of the girder, and that the girder will instead just roll. So, and then we can additionally consider lateral torsional roll buckling, which combines the two, where we say the girder is allowed to roll at the supports. It's no longer fixed to be straight upright, and it additionally has that twist component along the length of the girder as well.
Yeah, Hank, I think you answered the next question, but it wasn't so clear for me. I couldn't have repeated. Can you explain also that, therefore, does this method apply also to steel girders or not? Yeah,
that's another great question. Yes, there's nothing in this method that would prohibit it from applying to steel girders as well. We could do that analysis. Just the difference is that these sorts of lateral instability issues, particularly during transportation and handling, are not really as prominent of an issue with steel for a couple of reasons. One reason being that steel cross sections, their self-weight isn't as big of an issue while they're being transported and handled. And additionally, you might see different results, and generally different results than you would expect from concrete, due to the torsional stiffness of slender steel cross sections is much lower than the torsional stiffness of these relatively bulky concrete cross sections. So you might see larger torsional deformations in a steel girder that's transported and handled, as opposed to possibly larger roll deformations in a concrete one, but smaller twisting torsional deformations. And I hope that answers your question.
Yes, thank you very much. And again, thanks to presenters from University of Washington, Dr. Stanton and Hank,